Good morning. So today we are going to be starting lecture number 22. Last Wednesday I mentioned that last Wednesday would be the last time we'll discuss about architectures. That basically meant that we are not going to be discussing about any new layers, let's say, within PyTorch. We're not going to be discussing how we can combine them in different ways to construct architectures, either for sequence modeling or before that for CNNs and autoencoders. The next couple of weeks, this week specifically, is going to be about explainability within neural networks. Essentially, till now, we have discussed neural networks as these very large models. Some of them have more than 100, 150 different layers. All of them are acting non-linearly on top of a single data point and giving you some kind of results. The goal for this week, for today and Wednesday, is to discuss what methods there are in order to construct some kind of explanations regarding these neural networks. Next week, we will start with some different paradigms within learning itself. Like we have discussed supervised learning and unsupervised learning quite a bit. But after that, there are multiple different paradigms of learning, like self-supervised learning and active learning are two things we will discuss along with transfer learning. And if there is enough sufficient time, we'll just give small introductions towards like something like reinforcement learning, curriculum learning, and online learning. So that is like the general plan for the next couple of weeks until the semester ends. Quite a few of you have reached out regarding extra credit. I think about 9 of you reached out last week. So I'll release by the end of either today or tomorrow. We'll discuss what that. I'll make an announcement on Canvas and tell you what those extra credit is going to be. So the exam is going to be on May 1st. So this is only for in-person students. For distance learning students, I think everyone has chosen the project option. So there's going to be no exam for distance learning students. For in-person students, it's going to be on May 1st. It'll be slightly longer than the previous exams, like the 2 quizzes. Those were more for 75 minutes. This one is going to be for 90 minutes. Again, if you have chosen the project option, this is not something that is required for you. But if not, then it'll be on May 1st and it'll be for 90 minutes. Similar to previous quizzes, you'll have like a time window. This time it's going to be between 8 to 11 a.m. And you need to take that 90-minute time window within that time frame in order to take the quiz, essentially. All the other logistics are going to be very similar to what you did before in quiz 1, quiz 2. It's going to be there on Canvas. You can take it directly on that. And there will be an option to upload your scratch work at the very end, but of course it is not required. So you do have an option that if you have indicated, this is more for grad students. So if you have indicated in your project progress report that you want, let's say, you don't want to do the exam and you want to do the project 40%, then if you decide otherwise, please let me know. Email me before April 15th regarding your decision. For now, I'm taking everyone who has indicated that they want to take the exam on your project progress report. I'll use that in order to assign you, essentially. But if you don't want to do that, please let me know before April 15th, and we can go through and I can change that for you. Extra credit, as I said, I'll make an announcement either later today or tomorrow, but definitely before class on Wednesday. Yes? So there'll be no homework 8. There is a homework 7 left, which is going to be sometime today evening. It will be given out, and it's going to be due on Friday. 2 weeks from now, like a week from now, the Friday, like generally we do. Another thing is that there cannot be any kind of extensions. So in all previous homeworks have been very lenient in terms of the deadline extensions, but institute policy regarding the last week is very strict. So we need to complete all grading and give you back the grades before reading period starts, which implies that we need all the homeworks before Friday on that week, so that we can go through and grade them over the weekend and give you back. Same thing with the project assignments as well. So you have to submit your projects before the reading period starts, which is either the 22nd or 23rd, I believe. But when I create the assignment on Canvas, you'll see when that is going to be due. So that is the only, in terms of a very hard and a strict deadline. Homework number 7 and project has a hard and a strict deadline compared to all the other ones before. All right, so in terms of explainability, we have these 4 big topics that we're going to discuss. The first one is just definitions of what explainability is. Next ones are specifically within convolutional neural networks, how can we explain those architectures? We'll discuss the first 2 parts today. The next 2 parts, which is what types of explanations are available to us and how do we evaluate explanations when we have them, are 2 things that we're going to be discussing on Wednesday. So let's start with explainability. So there are many topics, there are many terminologies that are used when it comes to trying to understand neural networks. 2 big ones are interpretability and explainability. And the way we would differentiate interpretability from explainability is the idea that there's a human understandability that comes into picture. If my goal is to construct a good architecture, then just having some kind of a theoretical framework where I know that 5 neurons is going to be better than something like 10 neurons, let's say, then that is an interpretable part for constructing this neural network. But you want to explain neural networks and how they work to all human beings, people who understand what is the definition of a neuron, people who understand the definition of layers, or people who have no idea about the subject, who have no idea about, let's say, electrical engineering, computer science, or any of these topics. You should be able to explain it to them. So there's different hierarchies within explainability itself, but the most important one that connects everything is this idea of human understandable terms. We should be able to explain or justify our decisions essentially to all humans who ask it. So this is the main difference between something like interpretability, where you don't need to explain your answers or decision to human beings, versus something like explainability, where you have to have a certain class of methodologies that caters to all human beings, even if they are not in the field that you're working in. And this matters quite a bit, because let's say these deep learning algorithms that we have discussed till now are something that is going to be used by within autonomous driver settings, let's say, or insurance setting for your autonomous drivers. You cannot expect them to understand your mathematical equations and theoretical justifications in terms of, oh, these are my bounds. The error cannot exceed epsilon. That's usually how we do gradient descent, right? So if an error, basically, or a gradient, the norm of a gradient is less than a certain epsilon, which we say is a threshold, that's fine. Then we particularly say that this kind of gradient descent or our training is complete. But we don't need that. We shouldn't have something like that in terms of when we are trying to explain it to human beings who are in fact driving an autonomous vehicle. Same thing in medical settings as well. You have deep learning algorithms that help doctors and physicians essentially make certain decisions. So it can't just be a single number that comes in at the very end, because if you think of how physicians and doctors go through their decision process, there's like almost a flowchart to it. And this flowchart is not something that we can get from neural networks easily. So you need some kind of additional methodologies that accompany these neural networks in order to give you some kind of an explainable or a justifiable result, essentially. So deep models act as algorithms that take data and output something without being able to explain their methodology. This is how we have always seen neural networks until a few years back. We think of neural networks as this kind of a black box architecture where we give an input in the beginning, and at the very end, we expect some kind of output, let's say a 1000 cross 1 output that we get at the very end. And this is essentially why we have always said that neural networks are something of a black box models, where we don't really know what is happening within these billions of parameters that exist within a neural network. Right? When we were discussing something like logistic regression, for instance, it was very clear that the weights that were acting on top of my data point, on my features, were some kind of an important score on those features. Based on what those weights were, I could basically say that this particular feature has a 20% for the result, final decision. Fifth feature is the most important. It has almost a 20% weightage toward the final result versus something like the first feature, which would have just 5%. I could make these statements quite clearly in logistic regression, but when it comes to neural networks, I cannot do that because there's a lot of features in that interplay within each other. So this particular feature, let's say if you decide the first feature is 20% based on looking at the weights, that is going to be very different when you come to the second layer, because it's like the second layer now takes all your input, all your activations from first layer in nonlinear fashion, combines them and passes it on to the third layer, and so on and so forth, right? So there's no simple way for us to say what is important or what is not just by looking at these numbers themselves. That's why we need to come up with some explanatory methods. So in the second part of this, we are going to be discussing about visualization, what it means in terms of visualization of convolutional neural networks and features. So the first set of algorithms or methodologies that we look at in explainability is basically the layers. Are layers themselves explainable? And what are these layers essentially looking for is what we are going to discuss. Right? When we discussed autoencoders, this is something that we saw, but not deeply. We didn't go too deep and try to understand what it is for autoencoders, because again, the kind of autoencoders that we discussed were very plain and simple autoencoders, at least in the first lecture. So essentially, we looked at the entire image as if it's an entity by itself, like something within the MNIST dataset. But this is not usually the case in CNNs and other architectures, right? For instance, this image here is 224 cross 224. We cannot have convolution kernels which are this size. We cannot have convolution kernels which are 224 cross 224. We can have it for something like MNIST, which is just a 28 cross 28. So you can have a full kernel for 28 cross 28 that looks at the entire image of whatever the number within MNIST is. So your kernels, in fact, can look like the image itself. But that cannot be the case in these large-scale CNNs. So if I were to take your AlexNet kernel, which is 11 cross 11 cross 3, 3 is because the channels, if let's say it's working on an image, 11 cross 11 is the height and the width or the dimensions of your kernel itself, and 64 is the number of channels or the number of kernels that can exist. So if you were to look at a AlexNet architecture, your first layer would essentially have this. It's a 11 cross 11 kernel, and there are 3 channels. Sorry, I shouldn't call it channels, but these are the 3 filters associated with R, G, and B, and 64 is the number of channels or the number of kernels that can exist. If I were to take it and 11 cross 11 cross 3 is one kernel over here, and there's like 8 and there's 8 here. So there are 64 total kernels or channels. If I were to put them in these grid formations that we saw similar to autoencoders, this is how it would look like. So look at these filters that exist. Let me, if you zoom in, there are quite a few structures that you'll be able to make out. One is that in some of these kernels, there's a lot of just color structure that can exist. There's not much else you can differentiate from it, but there's color that can exist. There's green, there's purple. Again, the goal within CNNs, if you remember, is the stationary property, which is given a small set of basis for vectors or kernels, I'll be able to reconstruct the entire input image, or I'll be able to extract the important regions within a particular image, right? And you already know from the idea of primary colors, for instance, that you don't need the entire color palette in order to construct new colors or reconstruct back colors. Just having access to the primary colors, which are R, G, and B, is more than sufficient in order to reconstruct it. So what you notice within these neural networks is that it basically decides what the important, let's say, basis functions are or colors are, and those are the kernels that you're going to find. So these, for instance, are going to be the color kernels, and then there's going to be these kind of edges. If you have taken something like discrete cosine transform, discrete Fourier transform, those kind of classes, you'll know that in a 2D space, this is how these DCT and DFT coefficients might look like. This is essentially what your network is looking for in the earlier layers of a neural network. It's basically some kind of low-level edges, color blobs, textures, etc. which is essentially what your network is looking at. And again, this is only the first layer that we are visualizing in this particular case of your AlexNet. I think it's shown here as well. This is the first layer. So this is what an image is, this is what a network is going to look for within images. And later down the line, it's going to combine them in some kind of a nonlinear fashion to give you the output. But for now, this is the first layer, and this is what the network is looking for. So this exists across different architectures. So what we saw before was AlexNet. In ResNet 18 as well, the sizes are different, of course. So AlexNet has a very specific architecture, 11 cross 11 cross 3, and there's 64 kernels. ResNet basically has 7 cross 7 cross 3 with 64 kernels, and this is how the ResNet weights are going to look like. Again, very similar to what it was before within AlexNet, because there's not much changes that are happening within the images themselves, right? We are still training on the same kind of data set. I'm not sure I mentioned this, but all of these are the pre-trained models that you can get via Python. So it has been trained on the ImageNet architecture. So essentially the data set is the same, so you don't really need different kind of basis vectors in your first layer. It's only after that within ResNet you have these like skip connections and all these other kind of details within architecture, right? So, but initially there's not much change. The filters in the first convolution layers are going to look very similar, be it ResNet, be it AlexNet, or anything else. All right, so this is going to work very well in trying to understand what is happening. It's going to work very well when you're visualizing your weights in the first layer. But as soon as you start coming to the next layer, so remember, ResNet, there's 18 different layers, essentially, convolution layers that can exist, right? First layer, all in good. You've visualized it, it looks like this. But as soon as you start coming to the second layer, it's not as good. It's not as understandable in the second layer. And the reason is exactly what I mentioned before. You have used the first few kernels, the 64 kernels here, to extract, let's say, the different colors and edges. But after this point, it's just a set of activations, just a set of numbers, right? These numbers are the inputs into something like the second layer of your architecture. Unfortunately, those don't have as much of a spatial quality associated with it. So in the previous case, why it worked was because of the idea of spatial correlation that exists within your images. If you look at the color kernels, for instance, your edges, for instance, are based on different objects. These objects have different colors, and one side of that object is going to have one color, another side is going to have another color. Right? So it's looking for these kind of simple features, objects, and stuff that exists within these objects. But from the next one onwards, so your initial weights, if they look like this, your second set of weights is going to look very different to the first one. It's not something that is understandable easily when you directly look at the weights. If you read papers, let's say from pre-2013, 2012, then neural networks you'll see is that initial layers are going to be edges and colors. Next few layers are going to be a more abstraction of the concepts. Unfortunately, when it comes to these kind of large-scale neural networks, that does not exist anymore, especially once you have these millions and billions of parameters. Even from the second layer onwards, it's very hard to, in fact, say anything about what kind of template the filter is looking for. Question? Yes. It's still the same thing. That is still how a CNN works. It's just that we need better methods to explain that concept. So the concept is exactly the same. As we go through the layers within a CNN, it starts looking for a higher semantics of objects. So something like a computer screen can be nothing more than black and an edge in the first layer. But when you come to fifth layer, maybe there is an entire layer, let's say, a weight that visualizes the computer itself, the monitor itself, as the output. The difference to what I was saying there and what I'm saying now is that it's not easy to just visualize it. Just by visualizing the weights in some 20th layer, I'll not be able to make out that this is a monitor. Because at this point, it's like a very jumbled up, non-linear way of looking at your monitor essentially. And it's not very human interpretable, human explainable. So just by visualizing, let's say, these weights, I'll not be able to tell you what the object that this set of weights is looking for. So the concept of CNN has not changed. It's still exactly the same thing. It's just we are looking for ways to probe. We have ways to essentially probe this CNN to see how it's working, to see how we can explain it better. That's the only thing that has changed. The concept is still the same. As you go through, it still looks at more abstract concepts within the images. Maybe I misspoke. So kernels will be looking at all the entire 224 cross 224 because our receptive field, as it increases, it will look at the entire thing. But its input is not going to be the entire image, right? It's going to be some kind of a latent representation within this. So let's say this is the receptive field where it looks at the entire 224 cross 224. This here is just a bunch of numbers which may not have, in fact, a lot of spatial correlation to the original images that existed. So it's more a question of how do we explain or try to understand what is happening rather than saying that it's not looking at it or anything else like that. So that basically means that from the second layer and onwards, it's not just, we shouldn't just visualize the weights. So until this point, we have just taken the weights and visualized it. That's no longer an option for us when it comes to the next layers. So next, let's start looking at some kind of intermediate layers and essentially what intermediate layers might mean. The first thing that we can do is by looking at which of the convolution filters are being activated at what time. So let's say my image is this of a bus essentially, and I have a fifth convolution layer. Let's say within an AlexNet, I'm looking at the fifth convolution layer, and I'm going to be displaying all possible activations. So here what I'm displaying is the activations. In the previous one, what I was displaying was the weights, or we can call them the kernels or filters. But essentially before it was these weights, and right now I'm visualizing the activations. What I see is that it doesn't matter what kind of a bus or a vehicle I pass through, this particular kernel, the activations of this kernel here are always activated. There'll be this kind of a bright white spot that is going to exist within this framework. And what we notice is that this happens whenever there is this kind of a wheel that exists within an image. And this goes back to the question that you were asking, which is that yes, the existence of a wheel, you don't see it within the kernels, but it exists within these numbers, within these activations. That as soon as this kind of a wheel exists within an image, we know that in this conf5 activations, there is a single pixel within this conf5, there is a single number output within this conf5 activations that is always going to be high whenever we have these kind of wheels that might exist within my image space. Right? So weights may not be very interpretable, but in this case, the activations are going to be more interpretable, especially when we discuss the intermediate layers. So that was one method. Essentially, we're just discussing different methods of visualizing and explaining this. So instead of just visualizing the similar activations, we can also visualize what similar visual patterns basically cause this kind of maximal activations. So in Conf5, that was one example of the wheel, right? But there can be other examples as well. So each row corresponds to a particular neuron in Conf5. So for instance, if we have faces, this is essentially how it is going to look like. If we have certain numbers, this is what it's going to look like. The numbers here, 1.9, 0.8, 0.8, are essentially we are looking back at these activations and seeing, given a certain set of images, which number is going to be activated. Let's say, very simply put, this is one of those activations for numbers. This point here will have 0.8, I think I can write here, yes, 0.8, 0.9, 1, 0.8, and 0.8, right? So that essentially is what we are discussing right now. This is called maximally activating patches. So given a certain 0.9 or 1 or 0.8, you can go back and specifically say that this is the exact patch that has led to a 0.8 or 0.9 or 1 or any of these numbers that can exist. So you need to do this across a large number of images, of course. You can't just take a single image, pass it through, see what the activations look like, and then decide that, okay, this particular activation is a 1, and this exists because of this patch. You can't do that. You have to do it across a large number of images, and if a particular patch occurs, or if a similar kind of patches occurs in different images, and it always leads to, let's say, a 0.8, 0.9, or a 1 within your Con5 setup, then you can say that this is a maximally activating patch. So all these you can see all of them are different images, and we have done it across a different set of images in order to get our maximally activating patches. But this, of course, is not easy. So we already know that the size of our activations can be very large. In your quiz 2, I think you already had these, the number of activations, the size of activations, right, within a convolutional neural network. That, in fact, was a very, very simple architecture. But in these larger architectures, we can have millions of different activations within Con5 itself that can exist, or between different convolutional architectures. So we have to choose a Con5, we have to choose one of these activations, and then go back and check what are the maximally activating patches that can exist. So computationally, it might not be the most the best strategy, at least in terms of trying to analyze or explain our neural networks, because the number of intermediate layers are very, very large these days. So that brings us to the next stage, which is trying to visualize the last layer activations. So at this point, let's just, in order to differentiate from the intermediate, let's start calling them embeddings, but it's still, of course, activations. So by last layer, I essentially mean the fully connected layer that can exist. You've seen in most convolutional neural networks, or in CNN, or any kind of vision architectures or classification architectures, given a particular image, I have a large number of conv layers. Those would be followed by these kind of fully connected layers. Essentially, all the spatial convolution that you do is now going to be jumbled up even more within a fully connected layer to give you a single number at the very end, or at least a 1000 cross 1 vector at the very end, where each number tells you what the class is, or what the logit represents for a particular class. Again, if there are 1000 number of classes that you have trained for, which is true for ImageNet architectures. So last layer, what we can do is essentially we can look at these embeddings and try to visualize the embeddings rather than anything from the images. And the easiest thing that we can do, in fact, is basically look at similar images that now exist within the embedding space rather than within the input space. Again, to do this, what we would need to do is we would need to feed forward as many images as possible through the network and collect all the outputs from the final fully connected layer. Or maybe I should say all the outputs just before the final thing. So if this is, I don't know if this is very visible, but let's say this is 1000 cross 1. The one previous that is what we are interested in. So this is a 4096 cross 1. This is how many, this is the embedding that we get out of every image. From an architectural point of view, the final layer is going to be 4096 multiplied by 1000. This is the set of weights that can exist, but the number of neurons that is going to exist in the previous layers is 4096. Here it's going to be 1000, right? So this 4096 is essentially what we call by saying that this is the embedding that is going to exist from within a neural network. So let's say we get all these embeddings in the 4096 space, and we'll find the nearest embeddings for these images. So I'm going to take, let's say, 1000 different images. I'm going to pass through 1000 different images, and all these embeddings, there's going to be 4096 embeddings for each thing, right? So essentially what I can get is like a 1000 cross 1000 table. This is very similar to what we were doing in clustering before. When we had a k-means cluster on top of features, what we would construct is something like a 1000 cross 1000 matrix and just see what the distances are going to be. Maybe it wasn't 1,000 cross 1,000, but it was number of centroids multiplied by 1,000. So it's if there are 5 centroids, it's a 5 cross 1,000, and we would see what the distance is to every single centroid. Right? That is exactly what we are going to be doing here for last layer activation embedding. So it's going to be a 1,000 cross 1,000 in this case matrix, and we're going to look at the distance from every single embedding to every other embedding. And in the embedding space, it's not going to be similar to what we had in the original image space. Let's take an example here, for instance. So let's say one of the images that I'm looking for is this particular dog. The nearest image from an embedding space is going to be this dog. So even though our original dog on the left was facing a particular direction, the nearest embedding dog is facing the opposite direction. Now, semantically, these two are the same. It's still a dog, right, which is exactly what you want. But when it comes to input space, if you just do a very simple subtraction or an L2 distance between these two, it is going to be very high. And that is essentially what we were doing in k-means. We were not extracting any kind of a features. We were simply looking at the distance between our input images or features, right? But in this particular case, we have an embedding that is a very non-linear representation of our data, and just one subtraction from the other would give you this kind of like a simple methodology in order to say that these two images are equivalent when it comes to the last layer embedding within your representation space. So what you're calculating right now is this kind of a nearest neighbors, but not in the feature space, not in the input space, but rather within the embedding space. And now you can say that, let's say you are given a particular image during test time, and you want to know what this image is, why this image was classified as a dog. Well, you can point out to all the training images that exists. You can say that this particular training image was a dog, was classified as a dog, and these two are very similar together. Hence, I'll be classifying my current image during test time as a dog. So essentially, what we are doing is nearest neighbors, but not in pixel space, but in the embedding space that can exist. So that is one way of trying to visualize your final fully connected layer. But a different way can be directly visualizing this space, which is, let's say in this case, I have a 4096 cross 1. For every image, I have a 4096 cross 1 embedding, right? I need to take this and convert it into a space where I want to visualize it. And for us, the only way we can visualize something if it's within 3 dimensions. Anything more than that, it's impossible for us to visualize and try to understand. So let's say I want to do an even more harder case, which is I want to get it down to a 2-dimensional representation space, and that is something that can be done. So we are going to take the 4096 representation space, dimensional representation space, and we're going to convert it into a 2-dimensional or a 3-dimensional space. Now, there are many ways of doing this. PCA, for instance, is something that we have seen before. It's a very simple decomposition, let's say a SVD decomposition, but this time we are going to be making some kind of we are going to say that it's going to be based on variance. We need to find the largest variance, the axis with the largest variance, and use that as the dimensions, essentially, when we bring it down to a lower dimensional space. That is what we did with PCA. A better algorithm that is generally used is Tisney. And when I say a better algorithm, it's mainly that the properties are going to be different between PCA and Tisney, but we won't get into the math details of what Tisney is. But essentially, it's a methodology similar to PCA, where we are moving from a larger 4096 dimensional space to a 2-dimensional or a 3-dimensional representation space that can be easy to visualize. So that basically means that I can pass my 10,000 images from my MNIST dataset, the test images from my MNIST dataset, and if I pass it through a network, I get all my 4096 vectors. So in this case, the matrix is going to be 4096 cross 10,000, which is the size of my matrix. I will now convert it using Tisney into something like 4096 cross 2. Actually, no, that is incorrect. It's the opposite. It is 2 cross 10,000. and I'm now going to display this, and I'm going to literally just plot it on a graph. And this is what it's going to look like. Essentially, what you're seeing here is that all classes have their own embeddings. The color essentially represents the class over here. What you'll notice is that every single color, every single cluster basically essentially has some class associated with it, and you're now able to pick out your image. So if you're interested in one of these images, let's say at this particular point, you can point to this graph here and say that this image is now in the middle of all the other images that, let's say, have the class 6. Hence, my new image, I'm going to be classifying it as class 6. Right? So again, it's all methods of representation, which is, all methods of explainability, where I'm just going through and trying to find what the best explanation is or justification is for the class that my network has told me that this particular image belongs to. So in summary, in terms of what visualizing, the simple methods of visualization of CNNs, essentially what we have done is we have taken our filters or weights, and we have gone through and just visualized these filters and said that this is one good way of explaining our method. Another thing that we have done is looked at the activations. We have looked at our activations, gone back to the input space and said that given this patch of a wheel, this particular activation is almost always activated, which implies that if this activation is being activated a particular time, then that means that the input image has to have a certain patch associated with it. The way I said that implied causality, but actually that's not true. But essentially what it's telling you is that given a certain activation, if you know that that activation has a high value, then that means that there's a very high probability that there is a patch, like let's say tires or something else that can exist. The next one that we saw, so this was for the initial layers, which is literally the first layer. This was more for intermediate representations or intermediate layers. The last two things that we discussed was for last layers. So in last layers, there can be two of these methods that can exist. The first one is nearest neighbor images. So given a certain embedding, I can just do a very simple subtraction between these images and calculate what the nearest embedding is in a representation space, which is of course going to be different from an input space just because of the way that pixels work. And the last one is more of a brute force approach, where given my entire test set, I just pass it through my network and essentially just use some kind of a dimensionality reduction technique in order to plot them. And then say that, okay, this particular point exists within this larger cluster, hence it has this decision of, I think I used 6 as the decision, but yes, you can say that what class it belongs to based on that methodology. Again, there's a few things here, which is that within a neural network, which is a machine learning algorithm, I'm now using other machine learning algorithms on top of it. Right? I'm using something like nearest neighbors. I'm using something like PCA or Tesny. These we learned as separate algorithms by themselves, but we're using all these algorithms to explain this kind of a larger, more complicated algorithm, which is a neural network. We're making certain assumptions and using them to explain it. Any questions before we move to the next stage, which is saliency algorithms, saliency methods? All right, so now we move to the next stage, which is saliency methods. So until this point, we were looking at neural networks and just trying to probe what already exists. Given this kind of a very well-trained algorithm, we say that visualizing all these things helps us explain it. The next stage is we'll do some kind of interventions on top of our images to then say whether which patches are, let's say, more important. And we're going to be calling this a saliency via occlusion. So here's the main motivation of this. Given this image of an elephant, so my network has been completely trained. I've trained it for 5,000 epochs, let's say. It's a very, very well-trained algorithm. So during inference, what I do is instead of just showing this kind of a simple image of an elephant, I mask it. I intervene on top of it, and I mask it based on a certain value. So the mask itself is whatever the ImageNet mean and standard deviation is. I'm just going to construct this kind of a mask based on that standard deviation and mean of ImageNet, and place it at this point here. I'm going to pass the network. I'm going to pass the image back through the network, and I'm going to see what the probability is. Let's say I'm using some kind of a softmax layer to essentially see what my probability is. And at this case, let's say it's going to be 95% is the output when I mask the lower right part of the image. It still says P of elephant, so that means that the network has still said that the classification decision is still elephant, but the probability is 95%. Now let me move that mask. Instead of putting it in the lower right corner, I'm going to put it on top of the elephant, on top of the face of the elephant directly. So this means that now when I pass it through the network, my probability decreases to 75%. And the way we can think about this decrease is that the face was an important part of my elephant. For the network to classify it as an elephant, the face was very important. And hence, before, when the face was clearly visible, the result was 95%. Now when the face is not visible, the result is 75%, right? So again, it still classifies it as an elephant, but it's just that there is a reduction in terms of probability. From 95% has now gone down to something like 75%, which is the case here. Which means that these pixels affect decision more. It doesn't matter if I were going through and masking this portion, but if I were to mask the image face itself, the probability has now decreased by quite a lot, which is 20%, which tells me that these pixels are more important or affect my decisions more, essentially. So this is one way of thinking about how to construct these explanations via interventions. So I will take a mask at this point, and I'll see what my output is going to be. I will now shift it and create the mask at this point and see what my output is going to be. I can shift again to the next stage and see what my output is going to be. Using that, I can now create this kind of a heat map across the entire image based on just one, the probability itself. And that could be an explanation by itself, right? So that is essentially what we are discussing here. If I construct all these masks across the image, and I pass it across the image, similar to how you would do in a convolutional sense, the output that I'm going to get is this kind of a, you can either call it a heat map or a saliency map, where the value itself within the framework, within the heat map, tells me what the importance of those particular pixels are going to be. So let me, if I, yes. So here in this particular case, what you'll notice is that the drop in, or not the drop, the probability itself in a few regions is going to be high, right? So in this case, let me in a different color, you'll see that in this case, the probability is much lower. As you saw before, it was like 75%, right? But when you actually do it, the probability is much lower in these cases compared to something like this, where even if I mask my result, it's not going to change as much. The original result, the original probability is going to remain the same. So that means that this is not the most important set of pixels, while these pixels are a very important set of pixels for making the decision of an elephant. Now you can do the same thing with other images as well. So this is the image of a go-kart, and these are the important regions as told to you by a neural network. So essentially this is saliency via occlusion. We say it's occlusion because we are occluding certain portions of it, for instance by these large patches, and then deciding what the importance is based on the network telling us what the probability is going to be. And this is a very intuitive and an important way. I'm talking about this more from an image perspective, but this exists in all things. In LLMs, for instance, this is the best way. You can change your prompts and look back at what the output is going to be. Sometimes your LLMs don't always give you, they are very confident in incorrectly stating what their solutions are. And one simple way of making sure if that is true or not is by giving different prompts, like, I don't know, like active voice to passive voice, by changing certain words within the prompts and seeing if the output is still going to remain the same, or how that image is that output is going to change. Again, very naive way, but very, very intuitive in trying to understand how these neural networks work. The issue with this kind of occlusion-based methods is that it's very, very expensive, right? And it's not always clear regarding what the hyperparameters are going to be. So in this case, I'm just showing you this kind of a patch because it's easily visible, but I could have chosen a patch which is smaller. I could have chosen another kind of a patch, right? It's not always easy to tell you what the size of these patches is going to be. Next, these patches need to go in a certain order. So I need to start from this point here and then move, and this is where the stride comes into picture. So this can be a very, very expensive process in order to get a single explanation. Again, all of this it's done for a single image. This is not across a data set. It's done for just one single image. You need to construct these methods. It's a very good method in terms of it's very faithful to what the network thinks in terms of the important pixels are, but it's a very, very expensive method that might not always give you, that might not always be feasible when doing these kind of explanation methods. So we generally want to come up with a simpler set of methods to do something very similar to this. And this is where we'll start thinking about, okay, what exactly does this represent? And this is similar to what I mentioned before, which is the idea of feature importance. In logistic regression, your W weights were nothing more than an importance coefficients on your features. So given a certain X, you would multiply it with a W. A bias is something that it does not depend on the data itself. Sorry, it does not depend on the data itself. So W is the one that was choosing the importance weights on your data, and you had a sigma, which was essentially your nonlinear activation. But the most important part here is that the weights were importance. So we want to do something similar in neural networks as well, to come up with these kind of one-shot solutions to what the weights are going to be. And we make a very, very simple assumption, a very, very incorrect and a simple assumption, which is that what if my f theta was just a single layer with non-linearity associated with it. In other case, we have this kind of a very large input, and we don't care about anything that is happening in between. We just say that input and output is directly connected to each other just by a single simple layer. And this entire thing is just f of theta, essentially. If that were the case, then I can linearize this entire model. So even though there might be a nonlinearity for this one layer, I can still linearize it and say that based on some Taylor series approximation, around a certain value A, my output Y is going to be f of A plus f dash of A multiplied by something, f double dash of A multiplied by something, and so on. Right? So what this is essentially, given a certain non-linear kind of a line, you are approximating at a certain value that this is going to be linear, which is essentially what your gradients are doing, right? So this is what Taylor series essentially does, and we'll be saying that the simplest way for me to understand this kind of a non-linearity or to linearize this model is by having W equals dou Y by dou X. Very simply put, that's all it is going to be. That if I can get the quantity dou Y by dou X, then that is the importance of that particular X. So X, by the way, is, I think we have it here. So X is xi1, xi2, xi3, and so on. So it's essentially a vector. So in this case, it can be dou x1 or dou x2 or dou x3 or so on, right? So given a certain output, how much of that is being influenced by x1, x2, x3 is your importance weight. Again, it's a very, very big kind of approximation, but it makes sense that if there was some kind of a surrogate model which essentially took my input to my output in a single layer with one nonlinearity, then its weight would essentially be the importance score. So I'm just constructing a logistic regression algorithm, let's say, based on the inputs and outputs that are given by my neural network, which is essentially a surrogate model. And if we do that, then a backpropagated gradient, in this case W, is going to be my importance score. Right, so let's say I have an image of a dog, I pass it through, I get a y-cap, which is 0.05, 0.1, and 0.85 for a particular dog. If I now backpropagate it and compute the gradients and put it back into the same feature space, same input space, then I'm going to get the saliency map. Right? This is essentially what the previous slide was telling you. Your dou y divided by dou x, if you were able to get it, then it would look something like this, your saliency map, which is dou y cap c divided by dou x. And so if we compute the gradients with respect to the image pixels, which in this case is what capital X is going to be, then if we visualize the max value across the RGB channels, then this is what it is going to look like. Across RGB channel essentially means that you'll have this, right? From an image processing perspective, this is R, this is G, this is B. If you were to just take the maximum value across a single pixel, across RGB, and represent it, it would look something like this. And this would be kind of an explanation. If you were to ask me why this image would be classified as a dog, then the network is telling you that these are the regions why the network is classifying the image as a dog. Now, the good thing for this particular method, by just looking at gradients, is that it's very inexpensive. Just by a single forward pass and a single backward pass, you are now able to get your explanation, if you put it back, of course, in the input space. And you can do this across different images, by the way. So this was one example. There's multiple examples that we can have in terms of just showing you how the gradients are going to look like within the framework. And of course, you're doing this across each pixel. The good thing about doing across each pixel is that, in fact, explanations by themselves will have some kind of a weakly supervised segmentation ability. So given this kind of, I think here it's a snake, here it's this background snake, you can convert that now into a segmentation module. Right? You can now, given this kind of explanation, you know that these are the regions where the snake exists, so you're essentially segmenting out the regions of the snake. So it's like a weakly supervised segmentation where you don't have access to the labels for individual pixels. You have access to just one label here, which is that of a snake. And based on just that one image, one label, we are able to classify pixels within the image. And that's why it's called like a weakly supervised segmentation framework. Again, next week we are going to discuss all these other paradigms. Weakly supervised will be one of them. Another good thing about these saliency methods is that it helps us uncover biases. So if I were to ask you what this image is, and you tell me that it's a husky, essentially, if you were to ask the network why it was classified as either actually it's classified as a wolf, husky classified as wolf. Okay, so if you were to ask why this particular image is classified as a wolf, it would look at this and this region in order to say that this is where the classification may exist, right? But this is a very biased way of looking at why this image is that of a wolf. Like if you were to ask yourselves, of course you would probably look at the face and say that, okay, this is the reason why this image is being classified either as a husky or a wolf or so on. But in actuality, the network has looked at the snow that exists. It has constructed these kind of correlations which are very incorrect. This is not how you want your network to classify. Maybe the reason is because every single image within the original dataset has this kind of a snow whenever the wolf has been present within the image. So that means that the network has not really learned for the face of the wolf or the husky. It has basically learned the snow that can exist. Now this image is a husky, but since it's now present with snow, the network is just classifying it as a wolf. So now you see that there is some kind of a bias that the network has learned, and you can uncover these biases based on the some kind of explanations. In this case, some kind of saliency methods that we can construct. And explainability is very important in trying to uncover these kind of biases within the literature. All right, so Now let's look at the different methods within the backpropagation, the gradient-based methods itself. The simplest one is vanilla backpropagation, which is just what we saw. So you have a forward pass, and then you go backwards. And you basically display all the gradients with respect to the input space, which is dou y by dou x. And this is what it is going to look like. And if I zoom in, you should be able to see that there is some kind of a all the features with respect to the cat is being highlighted in this case. But again, this is one method of trying to construct these gradient-based explanations. The way gradient-based explanations, vanilla backpropagation works is very similar to, so if in forward pass, if I have a ReLU nonlinearity, let's say I have -1, -5, -7, and -3 as the activations. All these are going to become 0 in the next layer, right? So this is how ReLU activation works within a forward pass. The way it's going to work in a backward pass is given this kind of a set of, let's call this dou y by dou L5, which is the 5th layer. If I try to now go back with ReLU in my normal vanilla backpropagation, the network essentially stores where the zeros happened before and is going to zero out those regions. So 3 is going to become 0, -3 is going to become 0, but -2 that existed is going to remain a -2 when we are doing this kind of a backward pass in terms of vanilla backpropagation. Again, this is different from the training thing. So we have completely finished training. This is during the inference process. In order to explain our decision, we are constructing this kind of a backpropagation algorithm. It's very different from the training process. And vanilla backpropagation essentially wants to keep hold of all the zeros where your ReLU had made a 0 in your activations and is going to only make those particular elements in your activation as 0 in vanilla backpropagation. There are different variants of this. Next one is deconvolute backpropagation. This is similar to the segmentation module that we learned, the deconvolution procedure essentially. In this case, your 3 is going to remain a 3, your -3 is now going to be made a 0, your -1 is now going to be made a 0. Right? So the ReLU architecture is now working in such a way that given 5th layer activations, when we are now trying to backpropagate to 4th layer activations, I'm just going to put a ReLU in between. It's very simple. In vanilla backpropagation, you would have stored the values where ReLU was acting in the forward stage and using that in order to zero out the values. In deconvolute backpropagation, this is the when we discuss the convolutional autoencoder and the deconvolution, this is essentially what we were doing. We want to make all the -3s as 0. We're just putting a simple ReLU from 5th while we are going back to 4th. So this is another way of deconvolving. And generally, we get a cleaner saliency map. Now, by looking at this image, maybe that is not very apparent. But in more cases, if I were to show you other images, deconvolute generally gives a better, more cleaner map compared to something like a vanilla backpropagation. In this case, I think the eyes are very visible, right? This is all for the cat image. So this eyes, it was very visible in the previous case. So this is deconvolute backpropagation. A bit better way is by something called guided backpropagation. So both vanilla and deconvolute are kind of combined in this particular case. So in the vanilla backpropagation, what you did was during the forward pass, you kind of checked where the activations were negative and made them 0. You stored those values. In deconvolute, you were looking at the -1 portions and making that as 0 when you were going back within the backpropagation framework itself. In guided backpropagation, both of them are combined. So a lot more of your values are going to become 0 than not, essentially, within your visualization framework. So as you can see, the yellows are 0, that's coming from the deconvolute. The reds are 0, that is coming from the vanilla backpropagation. Or in other words, the yellows are coming from the ReLU in the backpropagation framework, while the reds are 0 because of ReLU in the forward propagation framework. And usually when you do this, you get one of the more cleaner kind of explanations. So in this case, I think the cat's face, for instance, is very visible compared to previous, right? Compared to other deconvolute and vanilla backpropagation. So usually guided backpropagation tends to be the cleanest among all the existing simple gradient-based backpropagation techniques. But there is a very important and a very problematic issue, let's say, with these kind of simple gradient-based methods. They're not really explaining stuff. They're just showing you what the importance is in terms of the decision process. So if I were to ask you, for this particular image, there are a couple of objects here, right? One is an airline and the other one is a bus. If I were to ask guided backpropagation why this image would be classified as something like an airplane, it would show here. If I were to ask the network why it classifies as a bus, it would show this particular explanation. Now you can see that there's no difference between the two things, which is an issue because it needs to be class discriminative. If there's more than one object within an image, it has to show why a particular image may be discriminated as, let's say, in this case, as an airline or as a bus separately. There's a lot more theoretical frameworks about guided backpropagation that show you that it's really not doing any kind of an explanation. It's not showing you an importance map. It's just reconstructing the input directly. That's it. It's not class discriminative in terms of it can't differentiate between an airline or a bus, but it's just reconstructing what the original inputs are going to be. And in the original inputs, this is playing a very prominent role. This portion here is playing a very prominent role. It doesn't matter if that is for airline or for bus, right? You can make some kind of a statement here. So for instance, this is a little bit more prominent compared to this region, and this portion here is a little bit less prominent than this region, but it's really not as effective. It's not a good explanation strategy that we can use for this kind of a decision-making process. And some of the problem is that it's usually noisy. So if I were to construct this here, so in the previous, for a given single cat image, yes, it was better than DConNet and it was better than vanilla backpropagation. But in this case, you can still see that there's some kind of noise when you backpropagate for guided backpropagation. Yes, question? Mm-hmm. I'll talk about that when we come to GradCam next. So essentially, let's say it classifies it as a dog. Your question is asking, how can we class discriminate? So how can we ask it why cat or something like that when it has not classified it as a cat? We backpropagate the logic. So I'll talk about that when I come to the next stage. I have slides for that, which is easier there. All right. So in terms of summary, we have looked at two types of saliency map generation. One was based on intervention based, and another one was gradient based. Both of them have their pros and cons. Your intervention based was very faithful. It was a good explanation, but it's very expensive, and it's not something that we can actually use. Gradient based explanations are more of an approximation of your features, feature importance. It's very computationally efficient, but it really does not reflect any kind of decision making process. So what we'll do is kind of combine these two things together, or maybe not these two things together, but rather we will extend the gradient based explanations to something called GradCam, which is gradient based class activation map. So instead of just looking at gradients, we also want to look at activations. The reason we want to look at activations is that we want it to be class discriminative and we want to preserve spatial information, right? So activations essentially give you that. If you look at, I don't know, the fifth convolution layer here, the outputs from different kernels in your convolutional layer are spatially correlated to each other. You don't have that in your backpropagation framework and gradients, but you do have that with an activation. So let's see if we can utilize these kind of classes, activations, in order to construct better explanations. So again, usually this method is also not very foolproof because there's some kind of hyperparameter you need to choose. You need to tell me where the activation needs to come from. In the previous gradient based, it was very simple. Do y by do x, and this is x is in the input layer essentially. But right now, we need to choose a activation layer from which we can construct our explanations. The general answer to this is that we almost always take the last convolution layer, because it has the most amount of information. It has the highest receptive field, so it has looked at the entire image in order to construct its activations. So let's try to use that set of activations. So the next few slides are going to go through the methodology of GradCam itself. Again, you have your CNN architecture has been completely well trained. It doesn't matter how much. Let's say you have trained it for 2,000 epochs, so it's one of the best trained architectures out there. And our goal now is to look at this image, this dog-cat image, to explain what the output is going to be. So we have the final last convolution layer, and after that is going to be these kind of final fully connected layers that can exist. So once we pass it through, we'll get some kind of an output, either a boxer or a bull mastiff, whichever the one this network is looking at. We're going to look at, we need to explain this particular decision. Now, the way we do it is we first forward pass the image. It passes through the CNN, which implies that it has passed through the last convolution layer, and it has passed through this fully connected layer, and we get this kind of an output. In this case, let's call it a boxer, and we start backpropagating that boxer. In this case, it is given by the blue line is a backpropagation, where the black line is the forward propagation. Based on this image, I think I can answer your previous question. So if you want to ask why boxer, you would backpropagate this logit. If you were to ask why cat, then you would backpropagate this logit. So you can backpropagate whichever logit you want. It doesn't have to be the prediction that can exist. And this occurs in guided backpropagation, deconnet, and all other things as well. So given a 1000 cross 1 vector, whichever vector I'm backpropagating, that is going to be y cap. So now you're going to be dou y cap divided by dou x. You'll go through and find that, right? Basically, you can backpropagate incorrect classes also if you want. It's perfectly legitimate to do something like that. So now, coming back to GradCam architecture. So I'm going to backpropagate whichever logit that I am interested in. And this particular logit, we are going to backpropagate it towards the last convolution layer. So let's say 5th convolution layer, I think we have been using that for AlexNet. If that is our last convolution layer, so we backpropagate until this point. In other words, it's going to be dou y cap by dou fc1 multiplied by dou fc1 by dou, actually this should have been fc2, fc1 multiplied by dou fc1 divided by dou L5. Right? Of course, this is not all of it. Here there is going to be some kind of activation as well, dou z, dou fc2 by dou z, but I'm just ignoring that. I'm just saying that I'm going to backpropagate it until the 5th convolution layer, which is going to be dou fc1 by dou L5, which is the important part for me. Now, I'm going to get the outputs, right? So what does it mean by I'll backpropagate it to 5th convolution layer? That means that I'm going to get this kind of a dou y by dou L5. Or maybe I should use A as my terminology I'll be using. So some activations in the 5th layer, I'm just going to be using that as dou y by dou A. So this is what you are going to get at this particular point. Now, what are we going to do with the gradients themselves? We are going to construct this kind of a weight for a particular channel by just adding up all the kernel gradients. So this red gradient here is now going to be added up into a single number, which is given by this one alpha 1 at this stage. The purple one, which is the second one, is going to give me alpha 2. The next one is going to be giving me alpha 3 and so on. So if I have 64 channels in the 5th convolution layer, the last convolution layer, then I'm going to get a vector which is 64 cross 1 vector. And this alpha is essentially my weight vector. I'm going to use my gradients to construct this weight vector, which is alpha. It shows you the scalar importance of kth feature map that exists within my last convolution layer, right? So based on that, all I'm going to be doing for getting my GradCam, LGradCam, is sigma alpha into AK. In other words, I'm going to use my gradients to construct a importance vector, which is alpha. I'm going to use that alpha back into the activations. right? Alpha is constructed using gradients. Now this alpha 1 is going to multiply my first A1. The last one here, alpha 64, is going to multiply A64. That is essentially what this is giving you. The alpha k multiplies your AK. Every single channel is multiplied by the weight vector or the importance vector, and at the very end you just add all of them. You just add all of them together. So all these 64 channels are just going to be added up together. That's it. You're going to look at each of the activation map, the channels within the activation, multiply it using the weights alpha, and just add them all together in order to get a particular matrix. At the end of the day, your LGradCam is just a matrix that is given by your the size of this convolution layer. Maybe for, I don't remember exactly, for VGG, it's 14 cross 14. So in the final last convolution layer, your output is going to be 14 cross 14, which is just a sum of all your activation multiplied by the gradient weights. That's it. And we, of course, have to now upsample it to the original image dimension. And if we do upsampling, we get this kind of output. So upsampling essentially goes from your 14 cross 14 in your VGG architecture. You need to go back to like 224 cross 224. In order to now bring it back to the same dimensions. And what you'll notice is that the output now focuses on the face of the dog in order to make your decision. And this is essentially what GradCam does. Any questions regarding the method of GradCam? It's very important. Your first question today in your homework number 7 is going to be about GradCam, and the second one is going to be another extension of GradCam that we'll discuss on Wednesday. But the methodology itself is very important. This is one of the most commonly cited papers for explaining decisions, especially in the visual space. And it's very simple in terms of computationally, it's very, very simple. And it usually gives you a good result regarding the explanation process itself. Another good thing about GradCam is that it's very generalizable. So this, what we discussed, was for image classification, but you could do the same thing for something like image captioning or VQA, which is visual question answering. You can construct the exact same method and you'll be able to get the output, because what you're interested in is the last convolution layer. Anything after this does not really matter. It could be a architecture for a object detection, it could be architecture for image classification, image captioning, it doesn't matter. You'll still be able to obtain back the gradients, you'll still be able to obtain these kind of alpha weights, your gradients, activations, and construct back this kind of GradCam framework. So the generalizability of it, or adaptability to different application, makes it a very, very nice algorithm for explainability. So there are different ways of the different, these are the different like examples of using GradCam versus guided backpropagation. I think this came out in 2017, 2018. So at the time, one of the best methods was guided backpropagation. So if you read this paper, it kind of compares itself to guided backpropagation. In almost all cases, it's a better methodology. So for instance, if the input is these, this image over here, and your goal is to recognize where the torch is, you'll see that the torch is supposed to be here, but if you look at guided backpropagation, it essentially shows you this. It reconstructs the important features in the input, and it shows you the bat, while GradCam shows you what is really true, which is where the torch is going to be. So there are different ways, methods of trying to construct these things. Same thing here as well. Even when maybe we don't have a good output, you'll still be able to see that the GradCam is generally showing you some kind of a result which is acceptable. So in this particular case, if your ground truth is volcano, if you look at this region here, maybe the network has looked at the wrong portion in order to make its decision, but this is something that is explainable, right? If you show that even when there is a wrong classification or a wrong result, if you show patches or regions within the image that is leading to that wrong decision, then maybe that is a different kind of explainability. It's not the right explainability, but basically it's showing you where your network has gone wrong, and you can use that in order to probe through and maybe construct a better algorithm and a better network. So even unreasonable predictions sometimes are justifiable by looking at these explainability methods. But yes, that is the last slide for today. On Wednesday, we'll go through 2 other explanation things that we have not discussed, the types of explanations and the evaluation of these explanations, apart from just visually looking at it.